matrix. What is S? S11, S12, S21, S22. If it is symmetric matrix, then S12 is equal to S21. Correct? That means these two off-diagonal entries, that is S12 and S2, are not different. So how many independent? S11, S22 and S12. Similarly, if I have 3x3 matrix S11, S12, S13, S21, S22, S23, S31, S32, S33, for symmetric matrix, this part must be equal to this part. So how many? 6. So 3 plus 3 is 6. Therefore, for n by n matrix, suppose I have n by n matrix, how many linearly independent components are there? That we have to compute. So for that, look at this. How many elements are there for n by n matrix totally? N square elements. Correct? So we have n square elements. And how many diagonal entries are there? N diagonal entries. So to compute these off-diagonal entries, what you should do? The total number of elements minus the diagonal entries. Correct? Off-diagonal elements. So therefore this is minus n gives the number of off-diagonal elements. Do you agree with this? The number of off-diagonal entries. So this is total number of elements in the n by n matrix. If I subtract by minus n, that is the number of elements in the matrix, diagonal entries, principal diagonal. So you get total number of off-diagonal entries. How many of them are independent here? Off-diagonal entries. Only one part is independent. Correct? What is? Yeah. So therefore, half of them is independent. Do you agree? So this part and this part are same if it is symmetric. Correct? So then what it means? We got this. Correct? Plus the diagonal entries give the number of independent parameters for symmetric matrix. Correct? So plus n gives the number of independent components or parameters for independent symmetric matrix. How much? N square minus n plus 2n. How much? This is 1 by 2 n into n plus 1. 1 by 2 n into n plus 1. So for symmetric matrix or symmetric tensor of rank 2, we have half n into n plus 1 independent parameters. You can check for 2-dimensional case, the 2 by 2 matrix, it is 3. Put n is equal to 2, you will get 3. For 3 by 3 matrix, it is 6. If you put n is equal to 3, you get 6. That will be the next step. Okay. The next is for skew symmetric matrix. How do you compute for skew symmetric matrix? So let me write down the skew symmetric matrix explicitly what I have done for symmetric. So if A is a skew symmetric matrix, that means minus AGI. Correct? So therefore, put n is equal to 2. N is equal to 2 is a 2 by 2 skew symmetric matrix. A11, A12, A21, A22. Now check what happened in the diagonal case. How do you get a diagonal entries for a matrix? Look at the diagonal entries. Row index and column index are same. Correct? If I put row index and column index as a string, this is put I is equal to j here. If I put I is equal to j, then it is So you bring up here, bring this one here, this is equal to 0, therefore AII is equal to 0. So all the principal diagonal entries are 0 for skew symmetric matrix. This is true for skew symmetric tensor. Same thing extended to tensors. So all the principal diagonal entries are 0. So this is 0, this is 0. And one more condition is that off diagonal entries are minus, correct? So we have a minus sign here. We have a minus sign here. Therefore, in 3 by 3 matrix, you can directly write this 0, 0, 0. Correct? And what is this? A12, A13, A23 minus A21 minus A31 minus A32. The trace of these matrices are 0. The trace is 0. For tensor it is true. Trace of this symmetric tensor, 6q symmetric tensor is 0. How many linearly independent elements? Only half diagonal, correct? No diagonal increase. The same calculation you can do to compute the number of off diagonal thing, that is half into n square minus n. That is the number of linearly independent elements for skew symmetry. So half n into n minus 1. Half n into n minus 1 linearly independent components or parameters for skew symmetric matrices or tensor of rank 2. Do you follow this?